Let's look at chemical reactions where a catalyst has been added. So adding a catalyst, this speeds up the reaction, and it does this by lowering the activation energy, and oftentimes it creates, instead of just a one-step reaction, it creates a multiple-step reaction. So the reaction pathway has actually changed, and overall that lowers the activation energy. A lot of times they draw the catalyzed reaction on top of the normal reaction. So you can see that in a catalyzed reaction, the activation energy is a lot lower. Because the activation energy is lower, then the reaction is sped up. Catalysts are added to the reaction, but they are not used up in the reaction. They actually get spat out of the reaction. So, and I tried to represent that here. So we add some sort of catalyst, I said it was an F, and we see that it gets spat out here. So in this way, you add a catalyst to the reaction and it will keep working until all the reactants have become products, and as long as those collisions are effective. So on this slide, we are going to be combining the intermediates that we talked about in these elementary stepped reactions, and also we are going to identify a catalyst. So we are given a rate law for this. It is the rate law is equal to NO2 squared. And so that does tell me that this is the slow step, because it looks like they wrote the rate law from step 1. So I know that this is the slow step. It's probably not important for this equation, but we can make that correlation. So can we identify any intermediates or any catalysts? So remember, intermediate occurs in the products and the reactants, and it gets used up in the reactions. So I see that I have an NO3 in step 1 as a product, so it's formed, but then it goes on and it is used up in step 2. So that's my intermediate, NO3. And let's just double check that there are no more other intermediates. And it doesn't look like that there are. So now let's look and identify, is there anything that is a catalyst? So in a catalyst, you'll see it at the beginning of the reaction, and it will be spat out at the end of the reaction. And I see that I do have a catalyst. It's right here. So it enters into the reaction, but then it is spat out. So NO2, this is my catalyst. I can write an overall equation for this. If you cancel out the intermediates and you cancel out the catalysts, then you should get an overall reaction. The last question here we've already answered. What can you say about the relative rates of steps 1 and 2? That because they gave me the rate law, I know what the slow step is. So we know that step 1 is slow, and we know that step 2 is fast. What happens to the activation energy in a catalyzed reaction? So let's look at this distribution curve. I see that these particles right here, they will form products because they are past that activation energy point. If I add a catalyst, what that's going to do is slide this over. So my catalyzed reaction, I am going to have more particles be able to form products because that activation energy is slid over. So how you represent a catalyst in this diagram is just to draw the line a little bit further over. When I have a catalyzed reaction, this does change the value of my rate law constant. And remember, only two things can change your rate law constant. So never concentration, but yes to temperature and yes to catalysts. Some different catalysts in our life and in industry. Platinum is used in the catalytic converter of the car. It is a heterogeneous catalyst because it's a solid and it allows some gaseous particles to be able to line up more effectively. So instead of producing a lot of carbon monoxide, which is very toxic to people and to animals and to living things, it will change that CO2 to carbon dioxide, which is a little bit better. Iron is used in the Haber process to convert nitrogen and hydrogen into ammonia, which is used to make artificial fertilizer. Platinum is also used in contact lens disinfectant discs. So if you have contact lenses, and if you ever use a hydrogen peroxide cleaner, there's a catalyst in the container, so that allows fizzing to occur, and that fizzing helps to clean the contacts mechanically. Also in photosynthesis, there is a magnesium complex that is a catalyst, or an enzyme is what it's called in living creatures, but that assists in photosynthesis. If you were to look at a graph right here to look at if it's catalyzed or uncatalyzed, the slope is often used to find that rate law constant, and you would see that the catalyzed reaction would be steeper in slope, the uncatalyzed less steeper. Looking at this potential energy diagram, we have a lot of things going on here, but you see that the line in red, that is the catalyzed reaction. We see that instead of just occurring in one step, it actually occurs in 2 steps. This overall lowers that activation energy, and I see that my slow step would be the first step. So you could draw this out. The activation energy of this first one is a lot lower than the second one. So this would be my slow step in my catalyzed reaction. So let's take what we've learned and let's write an overall reaction for this. So I can go and add them up, and I want to eliminate what's on each side, and I see that there is just an O on each side. So this would be my intermediate. And this doesn't look like there's a catalyst. There's nothing that enters into the reaction and then is spat out with the last step. So I can go ahead and just eliminate my intermediates, and I can add this up. So I have 2O3 goes to 3O2. That's my overall reaction. Let's look at this reaction and identify any catalysts or any intermediates and write an overall reaction. Let's look and see if anything is produced that is then used later on. I see that there's a NO2 on this side that later on gets used up. So there's my intermediate. And let's see, are there any catalysts? So it looks like this enters into the reaction and is spat out there. So there's my catalyst. And let's just double check that there are no other intermediates, anything that's produced that later on becomes a reactant. Oh yes, I see another intermediate. Another intermediate. This is produced that then goes on there. So there's my other intermediate. And so I think that we can just add this up. So let's add this up, our overall reaction. I have 2O3, and then on this side I have 3O2. Notice that this final reaction is very similar to the one the last slide, but this one has a catalyst that's added to it. So again, you get the same overall reaction, but just a different pathway. This one is a 3-step, when the slide before we only had 2 steps.